Chemistry in Society, Lecture Chapter 6, Gases, Liquids, Solids, and Intermolecular Forces. Speaking, Dr. Tania Cordova Santiago. In this chapter, we're going to learn about intermolecular forces, IMF, and how in differences, the impact, let's say, in the different states of matter. Talking about the properties of solids, liquids, and gases related to how much space is there in between atoms and molecules, and then differences between ionic and molecular substances. And we're going to be describing intermolecular forces, among them the dipole-dipole forces, dispersion forces, hydrogen bonds, uh, also the impact, the effects of intermolecular forces on properties such as melting point, boiling points. We're going to explain why nonpolar solutes tend to dissolve in nonpolar solvents and polar and ionic tend to dissolve in polar solvents. So also we're going to be talking about gases, the basic concepts of the kinetic molecular theory of gases, gas law, different gases law, name, description, the mathematical expression, and then how can we use those laws in calculation? For example, how to find one variable if the other variables are known. Then the combined gas law and the ideal gas law equation. And again, calculating one quantities, one is the others are known from that equation. Now, let's talk about states of matter. So we know matters is we can have solids, and in the solids, the particles are very close together and have fixed positions, so there is no movement or vibration. So um, also solids are having because of the not having that much movement in the fixed position. Solids tend to have like a fixed shape and volume. Liquids, however, molecules have more space in between them, and so they're more free to move. And liquids typically don't have a shape. They just have a definite volume, but they adopt the shape of the container. Finally, in the gas, the particles are very far apart and they move a lot faster than in the other two states of matter. But gases are compressible. They can you can apply measure in pressure and make it smaller volume. So the volume is variable. So no definite volume, no definite shape. Just depends on the container and the conditions. So the intermolecular forces is the how molecules interact between them among them. So what happens between molecule and another molecule in how are these forces in the different states of matter. So for example, if we have in the different state of the matter, we can have, for example, the here is ice can melt and become a liquid. Now in the solid, the intermolecular forces, because the molecules are much closer, they have some organization we need to supply energy to break those forces so that we go from the solid to the liquid state. And more so in the liquid, which is fluid, we have intermolecular forces. Different molecules are a little bit farther away. So this is a fluid, and as we apply energy to break those intermolecular forces, molecules can go into the gas phase. That process is evaporation. And in the gas phase, the molecules are more farther apart, now much weaker intermolecular forces. So, and then talking about those changes, then going from the gas, here the gas, to the liquid state, that process is called condensation. The opposite from liquid to the gas is called evaporation. Now, if the liquid it become a solid, that process is called freezing. So when you put, say, water in your fridge and become ice. So and the other way around, so if the solid becomes a liquid, that process is called melting. Now, some substances can go directly from solid to gas. That process is called sublimation. We see that, for example, in what we call dry ice, which is solid carbon dioxide. It spontaneously goes at standard room temperature and pressure, goes to gas. That process is a sublimation. And the opposite is called deposition. So from gas to solid. So now we have talked already. So melting point is the temperature at which the solid becomes a liquid. Now, the opposite is also true. That at the same temperature, the liquid becomes solid is at that very same temperature. And here another definition: the vaporization is the temperature at which the liquid becomes a gas. So we call the melting point that temperature of when that happens. So, for example, water boils at 100 Celsius. But also, so at that temperature, we have two phases, liquid and gas. Higher than that, we have gas. So the boiling point then is that specific temperature. Here is the plot of how the process goes. So on the y-axis we have the temperature. On the x-axis is the increasing energy of the sample. So here under we have the solids, so molecules are very close together, tight, and not much movement. Rigid is the same. So if you start heating up the solid, there is a point in which some uh, softening will occur and the solid starts to melt. When that happens, the temperature stays constant during the phase change. So while this is happening, you have two phases, solid and liquid, and temperature is constant. When everything has now melt and everything is a liquid, if you keep heating, then the liquid warms up to a point where it reaches the boiling point. At that temperature, the molecules of the liquid have enough energy to go to the gas phase. So the liquid starts to vaporize to go to the gas phase. And while we have the process liquid going into gas phase, the temperature remains constant and we have two phases coexistence of liquid and gas. When everything has converted into gas, at this point, we just having just gas, we keep heating, we just have warming and warming gas. And here, as you can see, the gas molecules are much farther apart, moving a lot faster than they are in the liquid. Okay, so let's go up here. Now we want to compare in this slide showing the comparison between the behavior of ionic and molecular substances. In previous chapter, we have talked about electrolytes, and electrolytes are substances that can conduct electricity. They can be molten or solution with ions. So an ionic substance behaves as an electrolyte, and when you do the circuit, say the sodium chloride is an ionic substance, so when it is dissolved in water, you will have positive and negative ions. So this will conduct electricity, and again, it is an electrolyte, and you can create the circuit, and the light bulb will light up. However, if you, for example, have this is methanol, molecules of methanol, dissolving water. Now, methanol is molecular. You don't have ions, so it's not able to conduct electricity. So the solution is not an electrolyte. So molecular substances are not electrolytes. Ionic substances behave as electrolytes and can conduct electricity. Now, let's talk about the intermolecular forces and the states of matter. Here we have a solid, which is an ionic solid, so sodium chloride. Here we have interactions between two different type of ion, a cation, sodium, and an ion, chloride. The intermolecular force here is electrostatic, so this is a very strong interaction. So attracted by the intermolecular force, ionic interaction, they form crystal lattices. And it is very organized and with almost no movement between the atoms. Just tiny, tiny vibration. Now, another force not as strong is the dipole forces. So some molecules have polar bonds. We have talked about polar bonds previously, and that is when we have a bond in a molecule in which the two atoms in that bond have different electronegativities. So here, fluorine is more electronegative than hydrogen, so we have the dipole going towards that chlorine. So notice that we have delta positive here. So more negative on the side. So it's like we have a negative end and a positive end. And because of that, molecules organize so that the negative end of this molecule is close to the positive in the other molecule. So that is an electrostatic attraction, but because it's not full charges, only partial charges, this is weaker and it is called then a dipole force. So again, molecules with dipole can organize like that and do this kind of a network. And example of molecules with a dipole, we have water. Remember that we have two polar bonds between hydrogen and oxygen. It's polarized, electrons more towards the oxygen, and these two vectors say add up, and we have a net dipole here. Say you add these two vectors, this molecule is polar. Now this is fluoromethane. The bonds between carbon and hydrogen is essentially nonpolar, but this is, in fluorine, is more electronegative than carbon. So we have a net dipole. What that means is that we will have in water some shape in which we will have where the oxygen is. It will be more delta negative. Um, Let me just, I'm going to erase it. I didn't like that drawing. Let me just make it here over to in the molecule. So if we have a dipole, let's do the shape kind of water like that. So this part will be delta negative, and we will have positive side on the two ends of where the hydrogen atom are. So we have this dipoles, and molecules can organize in such a way that the positive delta positive is close to the delta negative. Same here, we can represent that roughly with a dipole like that. Here, however, um, carbon tetrafluoride has four fluorine. This has no dipole. The all of the bonds are polar, but the sum of that gives you no dipole. And the same happens with carbon dioxide, CO2. So those molecules are not polar and they do not exhibit this type of intermolecular force. This is for molecules with a dipole. Other type of intermolecular force is a hydrogen bond. That's a stronger interaction than just essential dipole. It is a dipole, but it's stronger because the bonds between it is always formed between a hydrogen that is attracted to a very electronegative atom, such as nitrogen, oxygen, or fluorine. So this dipole, say, has much, say, more separation. So more delta positive here. So these bonds are stronger. This is, say, being very delta positive, and this much more negative, due again to the high polarity of this bond here. Say hydrogen fluoride a bit this way. You can check out the electronegativities of the Pauli's scale, but this is very large, meaning dipole, and so much so that when hydrogen is attached to any of these atoms, it forms these interactions, hydrogen bond. If we rank the intermolecular forces, we're going to say that ionic forces are the strongest. Then we have the hydrogen bonding, which are, say, very strong dipoles, special type. Hydrogen bonding. And then we will have dipole ranking, the three types that we have seen. So this is dipole, dipole. All right. So we have in water, for example, this is an extense network. And this process is dynamic. The bonds uh, break and form in the fluid. Now, there are other forces that are much weaker that are called London dispersion forces, LEF. So essentially, bonds have electrons. So here we have an organic molecule. This is a bond between carbon and carbon, another. But there are electrons. Each of these bonds have electrons. So when molecules get so close to um, another, say, electrons, they can polarize each other. So that's called an induced dipoles. These are fleeting dipoles. Because of that, these are much weaker. So this is the weakest of the intermolecular forces, but things add up. And so the strength of that is greater intermolecular force the larger the molecule is. For example, this is the only intermolecular force that we have in hydrocarbons. In molecules, them arranged like in packs, attracted that way. Again, these are induced dipoles, fleeting. Okay, now let's talk about intermolecular forces and solubility. Uh, in solution is a homogeneous mixture. So now think of salt, a spoon of salt, and put it in a glass of water. You stir it, it will dissolve. That is a solution, a homogeneous mixture. We know that there are molecules of water in sodium and chloride ions, but we don't see them. It's totally homogeneous. And so the solute is what we have dissolved, what disperses in the liquid. So in this case was sodium chloride. The solvent is the substance that is dispersing, the dissolving the other. So it's typically present in greater quantity. In our example, it would be water. Now, when something, say, if you consider, remember your sodium chloride example, notice that this is an ionic compound, so this is a very strong intermolecular force. So when it's dissolving water, the ions break apart, but these intermolecular forces are now replaced by other many interactions between the ions and the water. And they're somewhat similar in strength, so it compensates that. So that's the principle of like dissolve like. So typically, when things are ionic or very polar, their solutes tend to dissolve in a polar solvent. Water is a polar solvent. Sodium chloride is an ionic compound which dissolves in water. Glucose, for example, a sugar, has many bonds, has many bonds like that, OHs. And these are the carbon oxygen bond is polar, but not only that, it can form hydrogen bond. This H can form hydrogen bond with other molecules. So that in water, again, the hydrogen bond interaction is very good, let's say. And so sugar dissolves in water. So polar bonds containing many polar bonds, polar molecules and ionic. And substances that are not polar, say oil, these is mostly, say, if we have oil, say the ones that actually come from oil derivatives, they're basically made of chains of hydrocarbon, which are essentially carbon and hydrogen bonds. So not polar bonds. These substances are not polar and they will not dissolve in a polar solvent. However, they would in another non-polar solvent. So that's the principle of that, what we just said. Like dissolves like. If it is ionic or polar, it will dissolve in polar solvents such as water. If it is not polar, such as oil, for example, it will not dissolve in water. So here is an example of a vinaigrette, right? So oil not dissolving in the vinegar. And these are examples of solution, things that dissolve. This is wine, but in wine there are many compounds such as tannins and other things that give it the flavor. And you don't see those because being polar molecules, they dissolve in water. And in the oil that we put in our cars, this is a mix of different organic molecules, and it looks like homogeneous mixture because they dissolve one in the other, being similar in the structure, being nonpolar substances. Now, here is a picture of what happens when, say, salt dissolves in water. So here's your water molecule, the example that we were talking about. And here you have sodium cations and chloride anions. When the crystal lattice breaks, these are strong ionic forces. But as it breaks, it forms new interactions with the water molecules. The anion chloride, notice that it's surrounded by water, and also the positive, say, end of the water dipole is where the hydrogen is pointing now to the negative here. And the notice the orientation of the water molecules when interacting with the sodium cation is opposite because the where the oxygen is, that's the negative end of the dipole. So these are many of those interactions, dipole-dipole, in that kind of compensates in energy what is the ionic forces. So ionic compounds will dissolve in water. Now let's talk about gases. We have talked before about the states of matter. We know that gases in the gas phase, the molecules are very separated, and there's not a lot of intermolecular forces there since they are moving constantly and they're far apart, so moving rapidly. So these are the postulate of the kinetic theory of gas. First, the particles of a gas are rapid constant movement. So when you see this like tail, this is just showing, say, the molecules moving. And typically we you will see pictures with longer tails indicating more faster movement or shorter tails for slower. Anyhow, we this is assuming it is like that. So molecules are moving rapidly in the gas. Second, the molecules of the gas are tiny compared to the distances, so they are far apart. Then, because they are so far apart, there is little interaction between them. Not feeling much intermolecular forces. Another thing is here collisions between gas molecules are perfectly elastic. This is like imagine well, we are in a pool game and you have a stick and you hit the balls. Collision elastic is like is identical and they bounce back immediately. Say no loss in of energy in that collision. They keep moving and moving and colliding. And then the other thing that's important is that temperature is a measure of the average kinetic energy of the gas molecule. The higher the temperature, the faster the movement, or the other way around. So molecules moving faster, molecules of the gas means higher temperature, and moving slower is lower temperatures. Now, we're going to talk now about the gases law. One very important gas law is Boyle's law, and it says that the at constant temperatures, the experiment done at the same temperature, the volume of the gas is inversely proportional to the pressure. Or in other words, if you don't apply much pressure, the volume will be larger as we have here. But if you apply more pressure here, you put in more mass here. So pushing that down, the more pressure, the smaller the volume. You can increase the pressure here. You have 4 atmosphere represented by these 4 things. masses on the top. So more pressure, smaller volume. And that we can test that even in our experience. There are little balloons that you actually can compress with your hands. So, but if volume is inversely proportional to the temperature, there is a constant. Volume can be a constant times 1 over P. In solving, you can rewrite it this way. So PV equals a constant, meaning that we have the for the same number of moles, so P1, B1, P1 equals B2, P2. And so we can use that equation to calculate one thing if we have the other three parameters. This is a plot of what's happening. So it is inversely proportional. So as the pressure increases from P1 to P2, the volume decreases. And so pressure increases, I'm sorry, if you're increasing from P1 to P2, so you go from P1, small pressure, large volume, to P2, larger pressure, smaller volume. Now, another law, very important, is Charles' law, and it says that at constant pressure, now you're studying the relationship between volume and temperature. Uh, and we see that it is a direct proportionality. So the greater the temperature, the greater the volume. So if we have constant pressure, so that means instead of writing the proportionality symbol, we can do this equation where V is a constant. You can rewrite this equation and say that V over T is the constant V. And for different sets of conditions, you can say V1 over T1 equals V2 over T2. And here's a plot for such an experiment. You have volume in the y-axis, temperature in the x-axis, and what that is that, notice here, constant pressure. This is increasing direct relationship. So you have, as the um, temperature increases, say from left to right, increases this way, then the volume also increases. It's increasing in this direction. Let me see. Now, this is an experiment you guys can do at home, but not in the figure. What is a balloon, and you have like liquid nitrogen, and the volume will shrink. So this is the original size. It will shrink. I have done that experiment. You can do it and use these um, inflate balloon and put it in your fridge. And you will notice after several hours that it shrinks. You leave it a little longer, it shrinks even more. And then you take it out of the fridge and it will become larger. And so that is what is set here. So constant pressure, notice here the meter is pointing the same, constant pressure. The higher the temperature, the higher the volume. Now, here's Avogadro's law now. In Avogadro's law says that at a fixed temperature and pressure, the volume of the gas is directly proportional to the amount of gas. Remember the amount of gas, we talk about moles. That's our measurement of quantities. And so these quantities are directly proportionality between them. So we can rewrite this instead of being just proportional, add a proportionality constant C, and then rewrite the equation V over N, rearrange it, equals a constant C. And here we have the Avogadro's law then, is V1 over N1 equals V2 over N2. And you can do, say, calculation of V2 if you know the other three variables when you're running an experiment. In other words, you can predict what would happen using this. All the laws can be used that way. Now, for the gases law, we needed to find for for the next thing that we're going to be discussing, the ideal gas law, what we call the standard temperature and pressure. We have mentioned that before when for this concept. So in any 1 mole of gas at a standard temperature and pressure will occupy 22.4 liters. And gas temperature, the standard temperature is 0 Celsius, and the standard pressure is 1 atmosphere. Again, 1 mole of gas at that standard temperature and pressure, which we call STP. SCP. Okay. Now, this is the combined rate law. So here we have different laws. So Boyle's law, what it says, volume is inversely proportional to the pressure. Charles' law, volume is directly proportional to the temperature. This is Guy-Lussac law relating the pressure and the temperature. And you can combine all this law. Remember we saw this relationship before. If we work, let's say, if we work at constant temperature, for example, in the combined law, you can cancel those out. Here, then, you will have the relationship between pressure and volume, which is Boyle's law. And let's erase that. Now, if you work at constant volume, at constant, let's say, pressure, constant pressure, we can cancel those out, being the same. So you will have this relationship, inverse relationship between volume and temperature, which is Charles' law. And working at constant volume, you will have the Guy-Lussac's law. So this is a combined, when you include Avogadro's law, you have the N. So if you work in the whole expression of the combined law, can include the moles, as you see here, if you include Avogadro's law. But then again, if you work, as an example, at constant number of moles, you can cancel those n's. And if you work at the same temperature, meaning P1 equal V2, pressure is constant, you can cancel that out. This is what remains. And this is the relationship between a volume and temperature, and it is Charles' law. So that's your combined equation. And it's a good idea that we remember that equation and we do examples of those calculations. So this is now combining everything. We can now have another very important law, which is the ideal gas law. Remember, ideal gas is a gas in which the particles are very much separated, no forces between them, moving rapidly, masses tiny, and also distances are very large compared to the size of the particles. And elastic collision. That's what is the definition of an ideal gas. So, combining the equation that we saw before, we have then the ideal gas law where P is pressure, B volume, N is the number of moles. R is the gas constant. So these are 0, 10821 liter atmosphere over mole Kelvin. And so this is combining everything. And if you have, for example, a problem in which you're given temperature, the number of moles, in the pressure, you can calculate the volume. So you can have saloon that you have one of the things that you don't know, you can calculate all the other parameters. In this N, so N is always this constant. So you can, if you have PV, you can calculate uh, in N, the number of moles, you can calculate T and so on. Now, this is the summary of all these laws, and we will be using that in a lot of problems in chemistry. So having here, say for example, if you know V1 and V2 and P2, you can calculate V1 and so on. This is the summary of all this law.